In this section, we're going to discuss the maximum stress that rocks can take before they fail or yield in shear due to shear stresses. And in order to get started, we're going to first talk about what is called frictional strength. Probably you remember from your physics class that there are frictional forces that prevent, for example, in this case, this object to move. The force that you need to apply in this object in order to move laterally is going to depend on the normal stress and the friction coefficient between these two surfaces, the surface of the box and the surface in which this object is resting. You could run a test and you would see that the higher the normal stress, the higher is going to be the force needed to push this object, and there is going to be a proportionality coefficient between that, which is the friction coefficient mu. So if you have no normal stress, then the force needed to push this object is going to be zero. But if you have more and more stress or normal force, then you're going to require a higher and higher force in order to move this object. All right, so this equation actually comes after a little bit of algebraic steps when you consider this equation here, that tells you that shear stress tau is equal to the normal stress sigma n times the friction coefficient. So if we want to calculate what this force is, then we'll have to calculate sigma n. In this case of the box, sigma n is going to be the normal force divided by the area of contact, and we multiply that times mu, and we multiply that against the area in order to get the force and not the stress. So tau times the area is going to give us the total force. And you will see that the area is going to cancel out, so at the end of the day, we're going just to find the same equation that we have over here, that the proportionality coefficient between these two forces is going to be the friction coefficient. All right, let's take this concept now to rocks and to geological materials. And let's get started with a sandbag first. This is going to be just a bunch of grains, all of them together next to each other. And we are going to see something similar to what happens in the example of the box. But now the contacts are between grains, from grain to grain. And what I'm going to see and what is going to happen in this sandbag is that the higher the effective stresses that are pushing the grains next to each other, the higher the normal forces are going to be also between grains. And the higher the normal forces are between grains, the higher is going to be the force in friction needed to move this grain with respect to the other. And that, of course, is going to depend on the friction coefficient between the grains. What this is going to tell me at the end is that the force needed to move the grains with respect to each other and to cause an irrecoverable deformation in the sandbag is going to be proportional to the confining stress, effective confining stress in the sand, and also proportional to the friction coefficient. For example, a sand which doesn't have any effective confining stress, which is not subjected to any stresses on the grains, is going to have a shear strength which is equal to zero. And this is the example of a just let me go to this image. Oh, this one. If you have just sand, dry sand, as for example you might find on the beach, on surface you're going to see that this sand doesn't have any strength, and therefore because it doesn't have any strength, you can move the grains respect to each other and nothing is going to hold them together. This is what happens to, for example, if you make a pile of sand, the grains just roll on top of each other, and on the surface they are not going to have any strength. Okay, what about if we do have any stress? Well, if we do have any stress, the sand, which is uncemented, suddenly is going to have some strength and is going to resist forces that are not going to allow the sand to deform until you get to this maximum value at which the sand will start to deform. And that's a little bit more difficult to think or to see with naked eye, but I have a good example about this case. A case of an uncemented granular material which is quite strong, and you can purchase that in the supermarket. It's a package of coffee under vacuum. A package of coffee under vacuum has an effective stress which is equal to the atmospheric pressure. Why? Because inside the package it is subjected to vacuum, and because the vacuum is going to have what is equivalent a pore pressure equal to 0, and since it is under vacuum and outside we have atmospheric pressure on normal conditions, then the effective stress is going to be carried by an application of the atmospheric pressure through a membrane, which is the container, the plastic container of this package of coffee. That's going to push on the grains, and that's going to make this coffee inside the package to be quite strong. So next time that you go to the supermarket, try to find this coffee and under vacuum, and you will see that it pretty much looks like a brick, and it is pretty strong. I, for example, made a test in one class in which I stood up on top of the coffee package, and it wouldn't deform that much. This is how strong it can be. And remember that you can open the coffee package later and you will see that there is no cementation between the grains. All of the strength that this coffee package has, it is due to the effective stress caused by the atmospheric pressure applied through this membrane. All right, let's come back over here. And now if we try to write equations that will help us allow to understand what is the strength of this material, it's going to look very similar to the case we had before, but now I'm going to put this in terms of stresses. And what you see over here are more circles in which this is plotted with the shear stress in the y-axis and the normal effective stress on the x-axis. And here I also have the line which relates shear stress to effective normal stress through the friction coefficient, and basically tells me that the shear strength of the material is going to be proportional to the friction coefficient and the effective normal stress. Remember that the shear strength is the maximum stress that the material can take, in this case a shear stress. And this line is this line that I see over here. The slope is the friction coefficient. Okay, so let's see how this works and how we can relate it to the Mohr circle. The Mohr circle, it's just a plot of the state of stress in a given material. Let's take this example that we have here on the left. Here we have a sample which is subjected to a radial stress sigma r, effective stress, and an effective stress in axial direction sigma a. All right, what this line is telling me is that if I have a given radial stress sigma r, the maximum axial stress I can apply on this uncemented sand is going to be limited by the shear failure line. And in this case, this green circle for this given radial stress is going to tell me what is the maximum possible diameter of the circle for this given radial stress. And hopefully you can also notice that the higher the radial stress, or the higher the confining stress on this sediment, the higher the axial stress is going to be. For example, if I go from the green to the blue, you can see that the blue circle now has a higher initial radial stress, and because of that, is going to be able to resist a higher axial stress. And that both of those are going to be limited by the same equation, which is this shear yield line. Okay, the Mohr circle is going to have the principal stresses plotted in the x-axis, and along the circle we're going to have all the possible combinations of shear and effective normal stress, tau and sigma n, that are going to represent the state of stress at the given orientation in the Mohr circle. We're going to come back a little bit later to talk a little bit more in detail about how to build this Mohr circle. But for now, just remember that the Mohr circle is just telling us all the possible combinations of shear stress and effective normal stress. And once it gets to the maximum value, it's going to touch this line, and that's going to mean that if the Mohr circle is touching the line, the shear yield line at this point it is a failure, and that's also going to have a physical representation, which in this case is going to be a plane of failure within the sample. Okay, I have a few more examples to relate to this frictional strength of an uncemented sediment. We have seen that if we have a non-zero effective confining stress, in this case the radial stress, then this material is going to be strong, and that's going to depend on how much confining I have and what is the friction coefficient. Again, this is the reason why when I have an atmospheric pressure applied on a granular material, then granular material is going to be quite strong, and is going to resist any stress in another direction, which is going to be higher than that atmospheric pressure, and it's going to depend on the friction coefficient. Okay, what about, for example, if we don't have any effective confining stress, if this sigma r is equal to 0? Well, if sigma r is equal to 0, you can see right away from the plot that sigma a also is going to be equal to 0, and that's going to mean that this material cannot hold any shear stress. And again, this is the case of the uncemented loose sand without any confining stress, like for example here, dry sand on the beach, or for example the uncemented sand that could be located on the seafloor with zero effective stress. The strength is going to be 0. And that's also why when you try to dig a hole in the beach, when you get started, it's just pretty difficult to make a hole, and the sand is just going to fall into whatever you try to excavate. In order to make a hole in the beach, you have to go a little bit deeper so that you find the capillary water that helps you to keep this hole open. Otherwise, it can remain open. You cannot dig a wellbore in dry sand without the help of other forces. And we're going to see that this is quite important, for example, in drilling, that we're going to use the drilling mud in order to help us stabilize a wellbore. In this case, this wellbore is stable because of these capillary forces which are holding the grains together, and these are the same forces which, for example, hold a sand castle together. If you try to also to dig deeper than the water table, you are not going to be able to do it either, because you don't have any capillary forces anymore, and the hole is just going to collapse. If you take this to a drilling application again, uh, in order to drill a wellbore in an uncemented sand under the water table, we're going to need the help of drilling mud in order to apply an effective stress that is going to make the grain sands to hold to each other, and that drilling mud is going to apply an effective stress similar to what this membrane applies on the grains. All right, the friction coefficient that we get out of these uncemented sediments is a function of the properties of the grains, and usually in rock mechanics we quantify this through the friction coefficient itself, but also in other fields it's referred also in terms of the friction angle, and the friction angle is just going to be this angle over here, where the tangent of the angle is going to be the friction coefficient. And typical friction coefficients are in the order of 30 to 40 degrees, and typical friction angles range from 30 to 40, 45 degrees, and typical friction coefficients, which are the tangent of this angle, they vary from 0.4 to 1. Again, that depends on the properties of the surfaces which are in contact with each other. And the friction angle, probably it's something that you may have not heard about that before, but it has a very simple physical explanation and meaning, and this is related also to the angle of repose of an uncemented material. And this is what we see over here. If you have a pile of sand, you may wonder why that pile of sand doesn't just splash horizontally and moves just in horizontal direction. Well, the grains are able to form this pile and are able to pile onto top of each other because of the frictional forces. And the angle of repose, which is the angle from the horizontal plane to the angle of the slope, is related to this friction angle. The higher the friction angle, the steeper you can build a pile with an uncemented material. I have one more example to exemplify frictional strength. And frictional strength can happen between surfaces of grains, as we have here, for example, in an uncemented sand, or we could have in a sandstone, but also happen between surfaces of fractures. So if we have a fractured rock mass, also we're going to have a frictional strength between the fractures. And in this case, I have a video that I recorded some time ago in which I have two pieces of, actually there are several pieces of rock which are form fractures. You could interpret as a fracture. It's a so-cut piece of rock that it's not able to hold any stress at all in this condition. But what I'm doing in this case is I'm putting these pieces of rock into a bag that this bag is going to be subjected to vacuum, similar to the coffee. So notice that there, I'm picking up the rock. The sides are not glued to each other at all, and when I put it inside the vacuum bag and I apply vacuum, I'm going to be able to take advantage of the frictional strength of the surfaces of the rock. So let me advance a little bit further. Here I'm using the pump and I'm starting to apply vacuum. So now I'm going to have a stress applied on the surface of the rock, which is equal to atmospheric pressure. And after I do that, you can hopefully you can see how now the plastic bag, it attaches very nicely to the rock, and now actually it gets pretty strong, so strong that I can even go onto the table and stand up on top of the rock, and this is not going to move. Why? Because of the frictional strength between the surfaces of the rock. So there we go. I think just 1 second, enough. It moved a little bit, but you can see that still holds its shape because, again, of the frictional strength of the surfaces. We're going to see applications later on about how we can use this concept in order to calculate the frictional strength of faults.